Hi everyone, my name is Orna Paul, and I'm so excited to be sharing my presentation with you all today. My presentation is going to be on the future of solar energy, comparing two models of futuristic solar energy, orbital space-based solar power, or SBSP, and lunar-based solar power, or LBSP. So I would briefly like to thank my parents for their never-ending support and my mentor, Miss Sarah Anju. So we're going to be diving into their technological feasibility, energy transmission, cost effectiveness, environmental impact, and logistical complexity to see which model may be better suited to support humanity's growing energy needs in the future. To start, let's begin with the big picture. Why look beyond solar on Earth? So today, fossil fuels still dominate global energy. They're cheap, they're accessible, and they're powerful, but they also pollute, accelerate climate change, and are non-renewable. That's why there's been a major global shift toward renewables like solar and wind energy. However, even terrestrial solar energy has its limits. It only works when the sun is shining, so weather and the day-night cycle affect its reliability. That leads us to space. By moving solar collection off of Earth, we can bypass these limitations and potentially access constant 24-hour uninterrupted sunlight. So like I mentioned earlier, there are two leading concepts. In space-based solar power, we place these panels in Earth's orbit, collecting continuous sunlight and beaming that energy to Earth using either microwaves or lasers. Lunar-based solar power, on the other hand, places these panels on the moon using lunar materials to build the infrastructure of the solar farm. Power is transmitted from the moon to the Earth, bypassing Earth's atmosphere just like SBSP. Although both are innovative and futuristic, each comes with distinct technological and practical challenges. So let's compare how each model is feasible technologically. SBSP has access to perpetual sunlight in geostationary orbit, but the deployment is complex. Arrays need to be launched, assembled robotically, and protected from radiation, micrometeoroids, and temperature extremes. LBSP benefits from local resource utilization. For example, the silicon and lunar soil can be used to construct and manufacture some of the solar panels. However, the moon's low gravity can even make the construction easier for us. But lunar dust, temperature swings, and 14-day-long nights on the moon create major durability concerns. So SBSP may offer more continuous energy, but LBSP benefits from potential self-sufficiency and simpler deployment mechanics if its harsh environment can be managed. So when we go to energy transmission, both systems need to beam power all the way from space to Earth using either microwaves and lasers. Microwaves are efficient and they're proven, but they require large ground stations and raise safety concerns because we haven't explored what those could be on humans, on wildlife. However, lasers can be more precise and they require small receivers, but they are less efficient, especially over the long distances because they're disrupted by clouds, dust, and atmospheric conditions more easily. Even their effects on humans and wildlife are unknown as of now. So here, SBSP has a clear advantage solely because of its shorter transmission distance from orbit, which means less energy loss compared to the much greater distance from the moon. Now here in cost analysis is where differences really start to stand out. According to some NASA models, SBSP currently costs 61 cents to $1.59 per kilowatt hour, while the US household average is about 0.179 per kilowatt hour. So SPSP would need massive technological advancements like cheaper launches, longer lasting hardware, and more efficient energy transfer to even approach competitiveness. However, there is a sensitivity analysis done by NASA that shows that with the most optimistic advancements, tweaking certain factors, SBSP could reach a cost of 3 cents to 8 cents per kilowatt hour. Still, this requires simultaneous breakthroughs across multiple technologies. In contrast, and surprisingly, LBSP, based on rough estimates using SpaceX launch cost projections and panel efficiencies, could reach an LCOE of 15 or $0.015 to $0.032 per kilowatt hour, which is competitive with terrestrial renewables. This difference is mostly due to fewer atmospheric losses from the moon, a longer panel lifespan on the moon, and the potential to manufacture infrastructure locally that causes less cost to be taken from terrestrial sources. So each model has its environmental risks as well, because SBSP must contend with space debris collisions, radiation exposure, and the potential risks of microwave and laser beams aimed at Earth. It also requires massive ground stations, which could disrupt ecosystems and require large land areas. LBSP contends with these same factors as well as affecting a whole new environment, the moon. Mining and construction may create dust clouds, disrupt lunar landscapes, and damage heritage sites, or interfere with lunar scientific missions. So while SBSP poses more risks to Earth, LBSP's risks are more focused on the moon, though they're still significant and raise ethical and legal concerns. So as for logistical challenges, building and maintaining either system provides huge ones. SBSP has multiple rocket launches, robotic in-orbit assembly, complex satellite maintenance, and precise energy beam tracking. It is also vulnerable to space debris and repairs that are difficult to due to the system's location in orbit. LBSP, though potentially simpler to deploy thanks to lower gravity, has other issues like transporting materials all the way to the moon being very costly, lunar nights requiring energy storage or backup systems, and long distance transmission increasing energy loss. There are also legal uncertainties, especially regarding lunar land use, since the Outer Space Treaty prohibits nations from claiming ownership on the moon. So SBSP by comparison fits more neatly into existing satellite regulations. So, in conclusion, which model comes out on top? So, the simple answer is SBSP. In short term, SBSP appears more feasible, especially because launch technology and satellite transmissions are continuing to improve. However, it's not cost competitive just yet and is going to require many um, advancements in the future, both technologically um, and in just our basic understanding of these models. LBSP, while being more ambitious and still speculative, holds extraordinary long-term promise. If launch costs do drop significantly, as SpaceX predicts, and if infrastructure can be built using lunar materials, then LBSP could offer a clean, efficient, and cost-competitive energy source for Earth. In reality, both models offer incredible potential, and both highlight a key idea. The future of solar energy may lie beyond our planet. Thank you.
Thank you, Orna. So you do have some questions that came in. The first question is, at the beginning of your talk, you thanked your mentor, Sarah. I'd love to know, how did your mentor impact your project, and what is something new you learned from her?
Yeah, my mentor Sarah was very knowledgeable and very guiding. She works directly, well, she's a undergraduate at Caltech, but she works directly um, with like solar concepts. She's writing her own paper on solar energy right now. And so she had a vast array of knowledge to contribute to my project. But more specifically, she did really help with the research element. She provided many sources as well as her knowledge in the field because SPSP is a very like futuristic and not very explored topic. There were some NASA models, but a lot of it I was more like on my side for me to have to construct ideas. And she helped like put things into perspective and make assumptions and kind of help me understand what this could look like. So yeah, she was a really big part of this project and I couldn't have done it without her.
That's so lovely to hear. And the last question we have for you, Orna, is, well, first, congratulations on such a wonderful presentation and exploring the greener Earth. What is something that really stood out to you while doing your research?
That's a great question. Something that stood out to me, or something that was really surprising at least, was the fact that like right now, solar energy has so much potential, but it's very limited on Earth. And the fact that just taking it out into space could potentially give us like 24/7 uninterrupted energy was like completely mind-blowing to just think of a future where we have like constant uninterrupted sunlight, constant uninterrupted energy here on Earth that's completely renewable. So that was really amazing and really drove my interest for this project.
It sounds like this might be something you'll continue to, yeah, to explore further. Is that right?
Definitely.
Yeah.
Yeah, definitely.
Awesome. Well, thank you, Orna. You did a wonderful job.